Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
So this is a sample problem 5.8. You can see this is a simply supported beam that is supported at point A and point B. Clear? So there is a pin support and there is a rolling support, and there is uniformly distributed load of 20 kilonewton that is acting from point A till point B over the length of 3 meter. While at point C there is a concentrated load of 50 kilonewton that is acting downward. In problem, it is stated that a simply supported steel beam is to carry the distributed and concentrated load as shown, knowing that the allowable normal stress for the grade of steel to be used is 160 megapascal. So allowable stress is 160 megapascal, and we also stated that this allowable stress is either equal to or greater than the maximum, or we stated that maximum stress or maximum bending stress should less or equal to the allowable. So we are taking maximum allowable stress as 160 megapascal. So again maximum stress is 160 megapascal. Select the wide flange shape that should be used, and we have been asked to design a wide flange beam. So we have to select the wide flange beam by using our design parameter. We will design a beam that will be a wide flange beam. So in this problem you can see, first of all, for the problem to be solved, we have to define the stresses, reaction forces at point A and at point D. At point A there is a horizontal force as well as a vertical force, and at point D there is only reaction force, vertical reaction force. So RAY, RAX. Clear? So how you will solve this to find out the reaction force? So basically you will use the equilibrium condition, that sum of all forces along y direction is equal to 0, and sum of all the moments that must be equal to 0 about any point. So let's start. So as you know, there are the sum of all forces along x direction. There is only one force and there is no other force. Therefore, sum of all forces along x direction is equal to 0. So RAX will be equal to 0. So we will neglect this force. Only force that is acting in y direction is RAY, or you can also write simply RY, because the vertical force at point RA. Clear? So I will assume this force to be RA. So we will use first this equation. So sum of all forces along y direction must be equal to 0. So RA is the upward force, that will be positive. Now there is a uniformly distributed load that is acting at 3 meters. So 20 into 3 is 60, but it will be negative. So minus 60, and there is again a force of minus 50 plus RD will be equal to 0. So it means RA plus RD is equal to 110 kilonewton. So we will have one equation from this. Now sum of all the movement, let's say about point D, is equal to 0, and counterclockwise is taken as positive. So you can say there is one force RY that is producing a clockwise rotation. Clear? So RY into perpendicular distance is from this point to this point is 5 meter. So into 5, but it will be negative. Now there is a uniformly distributed load that is 60, and it is acting in the mid. This 60 is acting in the mid. So again perpendicular distance will be 1.5 plus 1 plus 1. So 112 and 3.5. So from this point to this point, this distance is 3.5. So again this is producing a counterclockwise rotation, so that will be positive. So 60 into 3.5. and there is a force 50 that is also producing counterclockwise. So 50 into perpendicular distance is equal to 1. Their sum must be equal to 0. So that will be 5 ry will be equal to 60 into 3.5. So let me calculate. 60 into 3.5 is 210 and plus 50. Clear? So ry is 5 ry is equal to 260. So 260 divided by 5 is equal to ry is equal to 52 kilo Newton. Now you have ry, you can this is ra, so ra, because it is acting upwards. So ra is 52. Now ra is 52, so rd will be equal to 110 minus 52. So when you will subtract 52 from 110, so rd will become equal to 58 kilo Newton. So this is how we calculate the reaction forces at end point. Now these are the solutions. So consider the entire beam as a free body diagram and determine the reaction forces at A and D. Then you have to develop the shear force and bending moment diagram. So for shear diagram, you will use the distributed load and as well as concentrated load and reaction forces to draw the shear force diagram, and then you have to diagram the bending moment diagram, so in order to determine the maximum bending moment. And then you will have a maximum bending moment. Clear? So you will use S minimum is equal to this divided by maximum or allowable bending stress. And once you have minimum section modulus, then you will go toward the table that is available at the appendix C of the book, and you will choose minimum section modulus, and against that you will choose the beam. I will show you in next few slides. So this was the beam, and this is how we calculated. We find out that D is equal to 58 kilonewton, and reaction force at at point A is 50 kilonewton. This is also solved here. Now how to draw the shear force diagram? So again you have to draw the two vertical lines from the end of the beam, and then you have to draw a horizontal line, and this horizontal line shows that the length of the beam along the x-axis. Clear? Now at point A you can see this is point A, and at point A there is only force that is acting is AY, and that is 52 kilonewton. So you have to take appropriate scale. You have to divide this vertical line into your into equal parts or as per your scale, and you have to plot 52 kilonewton. So this is the point where 52 kilonewton lies. So you at point A there is only shear force. On vertical axis we take shear force, and on horizontal axis we locate the length of the beam. So at point A there is only one force, that is 52 kilonewton, that is acting. Now we have to find if you use method of section or the method which we have discussed in earlier. So you have to take sections. Again it will consume too much time, so we will go toward the shorter we have to calculate it with a less time, with a less consuming time. So better is that this is point A where only 52 kilonewton is applied. Now at point B you can see that from point A to point B there is a uniformly distributed load, and this is this was 20 kilonewton. Clear? And this 20 kilonewton if we multiply it with the entire length over which this uniformly distributed load is occurring, so it will give you a concentrated load which is 60 Newton. So this is 20 kilonewton per meter uniformly distributed load. Now you can see, this is the uniformly distributed load over the length of 3 meter. So when you multiply 20 into 3, it will be 60 kilonewton. So area under this curve is the shear force. So area under this curve, this is 20 kilonewton per meter, and this is the length. This is the force, sorry, on vertical, this is the force, that is 20 kilonewton to meter, and this is the total length, this is 60. So at point B, there is 60 kilonewton force will be occurring. But remember that at point A there was a 50, so at point B there is a 60. So total, this is plus 52 and this is minus 60. So at point B there will be a minus 8 kilonewton, because at point B there is minus 60 and at point A there is a 52. So again 52 minus 60 will be minus 8. So at point B the shear force will be minus 8 kilonewton. Now you can see that the uniformly distributed load is a constant line having 0 degree. So shear force diagram will be the first degree line. So you can join them by using ruler. So when you join them, it will give you the shear force diagram. So at point E, there will be, at point E, it is obvious that at point E there will be no shear force. So shear force will be 0 at point E. So we will have two triangles. So one is this triangle and the second one is this triangle. Clear? So area under these triangles will give you the bending moment. Now from point B to C, you can see there is no force. So the shear stress will be same from point B to C, and that will be minus 8. So from point B to point C there will be minus 8. Now moving from point C to D, we can see at point C there is minus 8 and minus 8 to the left of point C. But when we go just forward from point C, so now there is also a force of 50 kilonewton. So that is minus 50. So minus 50 and minus 8. So it will be total minus 58. So from 0 you have to locate minus 58. So let's say this point is minus 58. So when moving from point C to the forward direction toward point D, so total shear force will be minus 58. Again from C to D there is no force. So from point C to point D there will be a constant shear force, that is minus 58 kilonewton. Now you can see at point D there is a minus 58 kilonewton, and from reaction which we have 58 kilonewton. So it means that your shear force diagram is correctly drawn. Okay, so we have drawn the shear force. Now we will require the maximum bending moment. We have to find the maximum bending moment. So for maximum bending moment, we have to draw the maximum bending, we have to draw the bending moment diagram as well. So one method is either you have to draw the bending moment diagram, or you can use this shear force diagram in order to find out the maximum bending moment. So we will solve both the method. You can see that at point A, the third method is that you have to find out the bending moment equation, and then from bending moment equation you will put the value of x and you will plot, but it will consume too much time. So better is to use a short method. So you can see that at point A there is a shear force that is 52 kilonewton, and it will pass through point A. So there will be Rx is equal to 0, so there will be no shear force. So at point A there is 0 bending moment. Clear? At point A there is a shear force of 50 kilonewton, but at point A there is no bending moment. Now at point, when you draw this shear force diagram between point A and point B, so a point where shear force will be 0. So if you have drawn it as per your scale, so you will you will measure this length, and this length will be x is equal to 2.6. This is one method. So at a length of 2.6 meter from point A, the shear force will be 0. So at point E, x is equal to 2.6. Also, you can see that from point A to E, the area under the shear force diagram is actually the bending moment value. So how you will find the bending value moment is that this is triangle. So area of triangle is equal to half of base into height. Now base is 2.6, so it will be equal to half of 2.6 multiplied by height is 52. So when you multiply it, it will give you 67.6. Again, it is written over here. So area under the shear force diagram between A and E is 67.6. So at point E, you have to plot the 67.6 as per your scale. So let's say this point is point E, and at this point it is 67.6. Clear? Bending moment is 67.6 kilonewton into meter. Now at point B, we have to find also the bending moment. So you can see that area under the line EB is the bending moment value. So how you will find the bending moment value? So you know that this length from E to B is, again, this is total from A to B, it is 3 meter. So from A to E is 2.6. So this length will be equal to 3 minus 2.6, which is 0.4. And this is length. Let me share. The area of this will be equal to half of base, which is 0.4, into height, which is 8. So again, this will be equal to 1.6. So this is 1.6. Again, this will be downward, minus 1.6, because it is minus. So it will be minus 1.6. So at point E, it was 66.7, and at point B, it is reducing minus 1.6. So at point B, it will be 67.6 minus 1.6, it will be equal to 66. At point C, as the area under the line BC is a rectangle, so its area will be equal to, area of rectangle is equal to B into H. So in this condition, B is length between BC, which is 1, and height is again minus 8, which is this. Clear? So that will be minus 8. So if you subtract minus minus 8 from 66, so it will be minus 58. Let's say this point is minus 58, or sorry, plus 58, because 66 minus 8 is plus 58. And from point C to D, again there is a constant, there is a rectangle, so length is 58 and height is length is minus 58 and height is height is minus 58 and length is 1. So area for this will be equal to 1 into minus 58, so which will be minus 58. So this is plus 58 and minus 58, that will be 0. So this is point E, this is point B, this is point C, and this is point D. Now you will have to join them. You can see that the shear force diagram between a line between point A and E is linear line, but slope is decreasing. So shear force diagram will be the second degree equation, and it will be counterclockwise. Now from point E to B, it is again a first degree line and slope is decreasing, so it will be again a curve. Now from point B to C, it is a constant line with 0 degrees, so shear force equation between D and bending moment line between B and D will be a straight line. and from C to D again it is a constant line or 0 degree line, so it will be again a linear line. So this is your bending moment diagram. So from this diagram you can see that maximum bending moment is 67.6. Maximum bending moment is 60, sorry, not stress. Maximum bending moment is 67.6 kilonewton into meter. This is how we can calculate the maximum bending moment by using bending moment equation. The second method is that you can easily find out that at this point shear force is 0. So maximum bending moment will be at this point. Clear? Which is x is equal to 2.6. And the area under this shear force diagram is bending moment, which is 67.6. Again you have found here it is 66, it is less, and again it is less, and again it is less. So 67.6 is the maximum, and you can find out the maximum bending stress moment from here. If you are confused that how this x is equal to 2.6 comes out, so we have another method. I will also show you. Let me erase something from here. So if you look at these two triangles, triangle A, let's say this point is A dash E, and triangle E B B dash, these are similar triangles. So by similar triangle means if we take the ratio of their corresponding sides, that will be equal. So if we take A dash, A dash over B dash, that will be equal to AE over EB. Clear? Let we do not know this distance, and we know that this distance is x. So obviously this distance is x, so this will be, if let's say this total distance is, this is x, so this will be x minus 3, because total distance is 3, so this will be x minus 3. Clear? So you have to put the value. A dash is 52, divided by B dash is 8, AE is x, and EB is x minus 3. So when you solve this, this x comes out to be 2.6. So at x is equal to 2.6, the bending stress, shear force will be 0. So bending stress will be maximum at x is equal to 2.6. So again, if you have the bending moment equation, so you will put x is equal to 2.6, and then it will give you the maximum bending stress. Either you know that at this point x is equal to 0, shear force is 0, so bending moment stress will be maximum at this point. So how you will find? You will find it by taking the area under this shear force diagram, so which is equal to half of this distance, which is 2.6, and this height, which is 52, and that is 67.6. Once you get this maximum bending moment, the value of this maximum bending moment, so you will have to use the formula of minimum section modulus. So let me erase all these things. So you can see that VA is equal to this, and VA minus VB minus VA is equal to area under the load curve, which is minus 60 kilonewton VB. All these things have been discussed, and we came to the point that at x is equal to 2.6, shear force is 0, and maximum bending moment is equal to area under the shear curves from A to E, and this was the area. This is a triangle, and the area is half of 2 into 52, which give you 67.6. Once you know the maximum stress, you know that minimum section modulus is equal to maximum bending moment divided by allowable stress, or maximum stress. So in this case, maximum bending moment is 67.6 kilonewton into meter, and maximum stress or allowable stress is 160 megapascal. So if you solve this and convert this into millimeter, so that will be 422.5 into 10 raised to power 3 cubic millimeter. So this is the section modulus, minimum section modulus required to be chosen. Okay, so from this section modulus we will see either the table that is available at the end of the book of W or short beam flange properties, and we will choose the beam, or we will have to go to market and we have to choose the beam having minimum section modulus 422.5 or greater than this. Always remember that you have to choose the minimum value is this one, so you cannot take the beam of section modulus less than this value. So you have to pick either this minimum value or you can go above this value. It will be the safer beam. But if you select a beam with a section modulus less than this value, so obviously it will be not safe and the beam can be failed. Clear? So let me show you the section modulus for the beam. So this is appendix C that are available at the end of big book. Also you have to see whether this whether you are selecting a property of a table having property in millimeters or in inch. So you can see here the properties are in inches, so you have to go toward the millimeter. So these are in millimeter. So the minimum section modulus was 422. So you have to select the minimum section modulus, that is 422. So you can see there is a value of 475. Let me zoom it. So there is a value of 475, that is W360 by 32.5. That is again maximum than 422. So you can select this value. You can select this. You can select this. All this. Clear? Again, if you go above let me check. Again 442 W10 W2442. So you can see this 416 which is less than, so you cannot select this beam, so you have to check. Also one more thing is to remember, just like now I have explained that you can use where is it? So you can use this W32.9 W360 multiplied by 39, and you can also use, so you can use all the beams of section modulus above 422 are equal to 422. But remember that in wide flange beam, this W360 multiplied by the second term, so this first value show you the height of the beam. Clear? This is W360 means it 360 millimeter height, and the second value show you the weight per unit length. So this 551 is kg per meter. Clear? So it is also written over here, a wide flange shape is designated by letter W followed by the nominal depth in millimeter and mass in kilogram per meter. So again this is 32.9 kg per meter, 39 kg per meter and 44. So you have to note down all the values of this section modulus. One more thing is, if you look at the table, there is two values, that is Sx and Sy. Section modulus is about x-axis and section modulus above y-axis. So if you look at the orientation of beam, the x-axis will be this one. So let's see, this will be like this. So usually our beams are usually positioned in this manner. So if your beams are not like this, if your beams are like something like in this orientation, so let's say this, if they are lying in this orientation, so again in this sense, this will be your y-axis. So for that you will have to select sy, but it is not mentioned in our problem, and we consider that beam are usually placed in this orientation, so that's why we are using the value of sx. Clear? So from that you have to choose the value of section modulus equal to 422 or above. So in our case, I have selected the different values of the beam. So you can see from this figure or from this slide, you can see we have minimum S values, and we have choose different beams that have values equal or greater than 422. So this W410 by 410 multiplied by 38.8 is having section modulus 637 Newton to the power 3 cubic millimeter. So this will have 474, this and this and this. So in all this you can see its values are greater than 422, but we will select the minimum, or we will select the value of S that will have less mass, because as a design engineer you have to also check the cost parameters. So you have to select the beams that will be cheaper as compared to the other beam. So if let's say if you select this, so definitely its weight is 38.8 kg per meter. So if you select this, now it has lesser mass than this. So if you compare these two, so the best choice is this one. Again you can go to this and this. Also you can check that from all these values, the lesser value of the beam weight per unit length is this one, 32.7. So if you look at this first and this value is section modulus value is the lowest of all. So if this, now we will compare this 1 and 2. So from 1 and 2 we can see that this beam have lowest section modulus and even closer to 422, and this 474 is higher than 422. But if we compare both these two, so we can see that the second value, this is 32.9 kg per meter, and this is 46.1 kg per meter. So obviously the weight of this wide flange beam will be very high as compared to this. So we will select this beam. At the end we will select this W360 into 32.9, and this is the best standard beam that you have selected, which meets your design criteria, i.e. the minimum section modulus will be greater than this, which is 474 into 10 to the power 3 cubic millimeter. So this is how we design the beam. Again I will repeat the I will conclude it that we will have a beam that will be under the given loading, and we have to ask to design the beam. So under the beam under the loading, we have to draw the shear force and bending moment diagram, or we have to only draw the shear force, and by using the shear force we can see where the shear force is minimum or zero. So at that point maximum bending moment will occur. So we have to find out the maximum bending moment, and when you have maximum bending moment, so you will use minimum is equal to bending moment maximum divided by allowable, so it will give you the minimum section modulus. Then you will have to go to the property tables of the beams that is available in book at the end of book as appendix C, and you have to search for the minimum section modulus beam. So from that table you can choose more than beams, but you have to check that it should have lesser mass per unit meter. Clear? So among them you will have to choose a one beam, and that one beam with meeting the criteria of minimum sectional modulus and minimum weight per meter will be your design beam, and you can use them as per your required loading. So this was all about how to design prismatic beam. If you have any question, you can ask in comment section. Thank you for watching. Again, if you like my video, kindly subscribe, like and watch. Thank you.